Welcome, and this is our last and final topic for today, which is the Hall effect. Hall effect is when a current carrying conductor is placed in a magnetic field. A potential difference is generated in a direction perpendicular to both the current and the magnetic field. This phenomenon is first observed by Edwin Hall in 1879, which is known as Hall effect. So you can see in our figure here that when I is in the direction of x direction, so ito yung I, and the magnetic field B is in the y direction, both the positive and the negatively charged carriers are deflected upward, making the force perpendicular to magnetic field B and its velocity. So Hall voltage is a sensitive voltmeter that can measure the potential difference generated across the conductor. So in our second figure is the sign of the Hall voltage depends on the sign of the charge carriers. So you can see na the edge becomes sufficient that there is a balance between electric force and magnetic force. That's why the charge carriers are no longer deflected. So in the figure A is the charge carrier are negative. So the upper conductor, which is C, becomes negatively charged and is lower electric potential than A. While on our figure B is when a charge carrier are positive, the upper edge becomes positively charged and it is at higher potential than A. So sa pag-derive ng expression sa Hall voltage, we can first note that the magnetic force exerted on the carriers has a magnitude QV, QVdB is equal and is in equal or equilibrium in electric force QEH is electric field of Hall, electric Hall. So therefore, QVdB is equals to QEH, and where EH is equals to VdB. So if D is the width of the conductor, yan yung width ng conductor, the Hall voltage equals to EHD, in which is also equals to VdBD. So we can obtain the charge carrier density N by measuring the current in the sample. So from equation 29.7 or 27.4 rather, the current average is equals to the change in charge over change in time, in which that equals to NQVD times area. So from that equation, derive natin yung drift speed, which is Vd is equals to current I over NQA, in which N is the measuring current of in the sample. So where A is a cross-sectional area, so yung A is cross-sectional area of the conductor. Substituting equation 29.20 sa 29.19, we can have equation 29.21. So since Vd is equals to current I over NQA, nalagay natin as I over NQA. And this equation is our equation 29.1. So that is the uh, whole voltage. But because A is equals to times 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 distance, the whole voltage is equals to RHIB over T, in which RH is equals to 1 over NQ, which is called the Hall coefficient. So we have an example here, which is the Hall effect for copper. So we have a rectangular copper strip 1.7 centimeter wide and 0.10 centimeter thick that carries a current of 5 ampere. Find the Hall voltage for 1.2 Tesla magnetic field applied in a direction perpendicular to strip. So since one electron per atom is available for conduction, we can find the charge carrier density in terms of molar mass M and the denser density P of copper. So N is equals to Avogadro's number over V, in which V is equals to molar mass over density of copper. So ito yung final equation natin for N. And the whole voltage from equation 29.22 is equals to IB over NQT. So substituting N, we will have the final equation of MIB over NA density P QT. And substituting the values, we have the molar mass, which is 0.0635 kilogram per mole. And we'll have the current, which is 5 ampere, the magnetic field, which is 1.2 Tesla, over the Avogadro's number, which is 6.02 times 10 raised to the power of 23 mole raised to the power of -1 times the density of copper, which is 8,920 kilogram per cubic meter, times the charge of is the charge, which is 1.60 times 10 raised to the power of -19 coulomb, and the T, which is 0.0010 meter. And we'll have the final answer of 0.44 micro. So that was it, guys. Thank you for listening, and I am your sixth reporter, Linus Richard E. Fernandez, and signing off.